Uh, so in our last discussion, we touched upon the spatial data formats, where we looked into raster and vector data formats. Continuing with that, we must understand that much of the description consists of investigating the properties of geographic features and determining the relationships between them. The chosen way of representing phenomena not only defines the apparent nature of geographic variation, but also the way in which geographic variation may be analyzed. Some objects, such as agricultural fields or even digital terrain models, etc., are represented in their natural state. Others are transformed from one spatial object class to another, as in the transformation of population data from individual point to census tract areas for relationship of confidentiality, convenience, or convention. The classification of spatial phenomena into object types is fundamentally dependent upon scale. For example, on a less detailed map of the world, New Delhi is represented as a zero-dimensional point. On a more detailed map, it will be represented as a two-dimensional area feature that we have discussed earlier also. So yet, if we visit the city, it is very much experienced as a three-dimensional entity, and virtual reality systems seek to represent it as such. So these features are represented through coordinates, so are lines in the form of lines, points, or area. So spatial data describes information that represents the physical location and shape of geometric objects as it is visible in this particular image which I have shared with you. The physical location and shape of geometric objects, these objects can be point locations, or they can be line or polygons or area entity. And complex multi-part collections of these types are represented here in this particular image. The spatial data is often accompanied by attribute data that provides more information about each geometric feature. For example, a point could represent a city, and the accompanying attribute could include the city's name, or what is the population of it, or how much area it is spread on. So a data model enables a computer to represent real geographical element as graphical elements. Two representational models are dominant. One is raster, which is grid based, and another is vector, which is line based. The spatial modeling helps a computer system show the geographic features in reality through graphics, as shown here. So vector created using lines, and raster which looks like a grid, as you can see in this particular image. As you can see, raster are based on cells that divide the map space into certain numbers of units, and all units are similar to each other, and in special cells have an individual coordinate xy and a corresponding value. That is, I am talking about the raster data. While the vector assumes the space on which the values are located in continuous, but on this you can see an infinite set of coordinates. You see in this image, the first left hand side, it is the ground reality. The second is the perceived land use which is visible in this particular image. And then the two are representing the vector model and the raster model, and lastly how they are represented in digital mode, that has been depicted. So while vector assumes that the space on which the value are located is continuous, based on this you can see an infinite set of coordinates. That is what I am referring to. So as we discussed in previous discussion, there can be three fundamental elements, and these are lines, points, and polygons. Points represents, line represents, point represents the smaller features. Lines are one-dimensional features, for example, river or railway line, etc. And area feature can be depicted as the land use would be the good example of it. So point represent features, line represent features created with points, and polygons are an area closed from all sides and have no exit. That is how we represent, we assume the polygon would be behaving like that. So here you can see as how the real world features are represented in represented spatially. This representation has three components. Now, very interestingly, if you see this image, one is the satellite image, and out of this satellite image, we have identified few point locations, few line locations, and few area locations, and depicted in three different sets of data. So here you see the representation has three components. One is the geometry. As I am saying, the geometry can be point, line, or area. So this geometry refers to the coordinates that define the shape of an object. Coordinates are often in the form of latitude, longitude for geographical data, or xy in a Cartesian coordinate system for local scale data, which we had discussed earlier. The another and very important feature of it is the topology. This describes the spatial relationship between connecting and adjacent features. Topological rules might specify that polygons should not overlap, or that lines must not be connected over each other, and they should be connected at both ends. So that kind of arrangement of representation of point, line, and area is very important in the context of topology. Another one is the attribute data. These are additional fields that describe the characteristic of spatial features such as name, as we have discussed in our previous slide, or any metrics that are relevant to the data set. For example, it can be the rainfall which is attributed to that particular location. So in this picture, point constitute the basic geometric entity representing singular locations on Earth's surface. Points are used to represent spatial characteristics of objects whose locations correspond to the single two-dimensional coordinates, that is xy, latitude and longitude. In the scale of particular application, for example, school or bus stop, etc. The lines represent objects having length, such as roads or rivers, as I am saying again and again, whose spatial characteristics can be approximated by sequence of connected lines, as you might have seen in the previous slide. And polygons are used to represent characteristics of objects that have boundary, like in land use class, parks, housing society, etc. So this is how we represent the geographic details in the form of point, line, and area features in digital mode. And that happens in two ways. One is the raster format, one is through raster format, and another is through vector format. So here you can understand as to how we can represent this spatial data, the same spatial data in raster and vector format. Now in this image, again the same satellite image where I have picked out one highway, which is the ground reality of the Earth, which has been depicted in both of these two formats. One is the vector format and another is the raster format. And you can see that here the vector format represents specific features on the Earth's surface and assign attribute to those features. Vectors are composed of discrete geometric locations, and as you can see in this upper left image, that it has specific xy values, and these values are assigned to each vertices. So there are 4 vertices visible in this particular image, and we have 4 xy coordinates. Now these vertices define the shape of the spatial object. The organization of the vertices determine the type of vector that we are working with. For example, if we are working with only point data or point area, point feature is being represented, then there would be only one coordinate, one vertex, that would be xy coordinate, that would be representing xy coordinate. But if it is a line, then in this case, as you can find, that we can have many vertices and many coordinates. And if it is a polygon, then the polygon would be closed line, and it might have many vertices, many edges which will have specific geographic coordinates. On the contrary, if you see the bottom left image where raster format is represented, so the raster format is any pixelated or gridded data where each pixel is associated with spatial geographical location. Now here you see that the ground reality is about an highway. So the highway is being depicted in this raster format. So this bottom example shows we represent any ground reality in raster format where a raster is accompanied by spatial information that connects the data to a particular location. This includes the raster extent and cell size, the number of rows and columns, and its coordinate reference system. The main difference between the raster and vector data is that the raster data represents data as a cell or a grid matrix, while vector data represents data using sequential point or vertices. Now again, the same raster and vector format has been represented here. The method of representing geographic features by the basic graphical elements of point, line and polygon is said to be the vector method or vector data model, and the data are called vector data. Related vector data are always organized by themes, and you may also understand it by layers, which are also referred as layers or coverages. For themes covering a very large geographic area, the data are always divided into tiles so that they can manage more easily. A tile is the digital equivalent of an individual map in a map series. A tile is uniquely identified by a file name that we are saying as layers also. A collection of themes of vector data covering the same geographic area and serving the common needs of a multiple users constitute the spatial component of geographic database. Now here you can see that how in vector format a line information is stored in the form of its latitude and longitude, where the latitude and longitude of each vertices are represented here. On the other hand, the raster data, we are having each pixel's information systematically arranged so that the same geographic realities can be represented in the raster data. Now, if there are many types of information which we want to store in any geographical representation, then we need to have it in different layers, and that is what we wanted to explain in this particular slide. So now we are focusing on the raster data format. So the raster data model is composed of a regular grid of cells in specific sequence, and each cell within a grid holds a data. The conventional sequence is row by row, which may start from top left corner in Cartesian method. In this model, basic building block is the cell. The representation of geographic feature in this model is used by coordinate, and every location corresponds to a cell. So each cell contains a single value and is independently addressed with the value of an attribute. One set of cells and associated value is a layer, as we have discussed in the previous slide also. And cells are arranged in layers. A data set can be composed of many layers covering the same geographical areas. For example, one layer may be representing the water bodies of any area, another may be representing built up area, another can be the forest area or agricultural land, etc. And all of them would be of the same geographic extent, which would be represented in the grid, in the form of grid cells. Now, if you can see this image, which we may be looking in detail and in enlarged form in the coming slides, but here if you can see, you can very easily understand that how the grid pixels are arranged and how the geographic realities are represented in raster format in the form of grid cell. Now, if I can explain it more easily, you can understand that these grid cells represents as a graph paper. You might have used graph paper in your all kinds of studies earlier. The raster data format is actually the same as the grid, as the graph paper. So that is how the geographic realities are represented in raster data format. So now you can see that how we highlight, how we can depict the raster data format. This is a structure of a grid, structure of a raster data format. Now here you can very easily understand what I mean with resolution. Resolution is about one grid cell. The size of this grid cell would represent the resolution, and the extent of the grid can be seen over here, from here, this side to this side, from x on x-axis, whereas the grid extent is also in the form of y-axis. So we have rows as well as columns, and one grid cell size is represented as highlighted here in this structure of a grid. So if I can explain the raster data, I would say that raster data is made up of pixels, as I am calling it as grid cells. So raster looks like pixelated because each pixel has its own value or class. Now I would remind you that earlier also I have highlighted this issue, that each grid cell will be carrying three kinds of information. One is about its location on x-axis or on latitude, in the context of latitude. Another would be on the y-axis, which might be in the context of longitude. So latitude, longitude would be the two information of any grid cell. And then we also know that each grid cell would be representing any geographic reality in one layer. So that layer would be represented by the appropriate attribute information which we want to depict in our digital data in raster format. So that is what the basic idea of raster data. So raster data, as I am saying, it consists of pixels. Each pixel has an associated value. A grid cell represents this data, as I am saying about the attribute data. In other words, it is a matrix of cells organized in rows and columns, as you can see here, in the form of rows and columns. Each cell has a value that represents the information. Again, I am trying to highlight that this is about the attribute information. Apart from attribute information, it's locational information which will correspond to the Earth location would be the latitude and longitude information, which each grid cell would be representing. This is a very good example of raster data format. One grid cell is the resolution, which is the minimum area or spatial extent which can be represented in this specific raster data format. So here a point data would be represented by one pixel, as you can see here, which has been highlighted here. So the point data would be represented by 1 pixel and one grid as filled, which is represented here. The point data is represented as a zero dimensional with its extent, if you recall, I have mentioned this, and it is depicted it in zero dimension only, but only by one pixel or the grid. Now, this is a good example of raster data format representing a line feature. As you are aware now that the line feature is having length but not the width. Hence, it is called as one-dimensional feature. They are used to represent linear entities such as river, road, etc. So now how this line feature can be depicted in raster model, you can very easily understand. So here you can see that how each pixel is representing one cell, one location over the ground, which is representing one location, one pixel of the ground reality, and it is a linear feature. So the line feature is a set of connected ordered coordinate representing the linear shape of a map. Object that may be too narrow to display as an area. You recall in my previous talk also I have talked about that how the scale would play an important role in identifying the point, line and area features. So even a line feature, it might have an area, but depending on the resolution of the grid data or raster data, or depending on the resolution of the ground realities, we might be depicting it as line feature, or even it might be represented as area feature. But here in this case, it is a line feature, for example, as an road with no width in this particular case. So in raster format, it would be represented like this, as it is being depicted in this particular image, where a linear feature is represented in a series of pixels represented this in this raster model. So this is very interesting, that you need to understand that how the raster grid cell resolution would play an important role in depicting any ground phenomena into the digital format. Now this is the example of an area feature, how in raster data format an area feature can be represented. So this is a good example of raster data format representing an area feature. Area objects, as you have now understood, that it has two dimensions of length and width. An area feature is closed figure where boundary encloses homogeneous characteristics. It can be a lake feature or it can be a soil type, etc. An area is delineated by a polygon, but this may be in the vector format. But here it will be represented in the form of a group of pixels which would be representing an area feature. So here an area feature is represented in a series of pixels represented in this raster data. This can be understood with this image now, where a point, line, area have been shown. Now you can see this is a good example where all three have been depicted in this particular slide, where point is being represented by one pixel, line would be with a series of pixels which are in linear mode and would be representing any linear ground reality, any linear entity. Whereas a polygon would be a group of pixels, would be representing depending on the resolution of raster data as well as the size of ground feature. So this is how point, line and area, all of them, they are depicted in one grid cell, in one raster data format, representing the grids, representing the cells in the form of point, line and polygon. Now this is again very important and very interesting example which I have tried to share with you. You see, I said that the ground realities have to be depicted in the form of raster data. So now if the ground reality is very large and we are using ratio scale where the ratio is very high, so there this problem may not be so prominent. But just to understand as to how we can represent the ground realities onto the grid data, it is very interesting to understand as to how each grid cell would be assigned any ground phenomena or any feature or any attribute information to each grid. So you can understand how to manage the resolution aspect or if the ground feature is smaller or resolution of data is finer, the pixel representation needs to be sorted out. This do not happen with the coarse resolution, but still the system needs to be assigned instructions because we are talking about the digital data. So the system needs to be assigned instructions how to pick feature in any raster format. So this is a very simple generic example, but good to understand, especially the resolution aspect of digital data. So here you can see that if we take the dominant attribute information in each grid, for example, our focus is on water area. This entire image is showing two land use classes. One is the ground data and another is the water body. So if we take wherever in the grid water is dominating, so this would be the example which would be coming. This would be the assigned attribute for only 3x3 grid. This way you can understand. But if you take dominating land use, then this middle attribute assigned would be taken as an example. And if edge separates, if you take that way of representation of attribute information, then the result would be like this. Now you see what we do, we assign this to the system, that how they have to pick the attribute information in the raster data format. So whatever the pre-decided assigned system to the digital data, they would pick the information accordingly and assign the value accordingly. So the raster data is simple, there is no doubt about it. They are easier to stimulate as all the cells are of the same size and same shape. But on the other hand, raster data can cause information loss. This example will give you a good idea how and why. You just think about it later and you would find that how the raster data, if any method we are using for assigning the attribute information, if there is any discrepancy there, then it might result into offering the digital data in containing some kind of error. That's an important issue with the raster data. But what happens generally, we are using some scale where the ratio value is much higher. So all this may be eliminated. It won't be such a big issue. But just to understand as to how the raster data is incorporated in digital mode, this you need to understand as to how we assign the attribute in the raster data. Now, this is again a very interesting example where I am trying to highlight as what is the impact of the resolution, or in other words, I would say that what is the effect of the grid size on data in the raster format. In this slide, the example which is being shown, the same data with larger pixel size would have distortion in shape and error in area calculation. But it gets better with smaller pixel size or with better resolution, both in terms of its shape and also in terms of the area which we might be calculating, because it is the spatial information which we want to depict in the digital format. So the relationship between cell size and the number of cells is expressed as resolution of the raster, which is very clearly you can understand as to what is the importance of resolution in raster data. As I am saying, a finer resolution gives a more accurate and better quality and better shape representation of digital data. Not only shape but also area calculation wise also it will give a better results, where this simple exercise you can do on your own also. For example, if you take, as I have said, that the raster data format is well represented by a graph paper. So what I will advise you, and I will give you a task, that you just take two graph paper. One can be a centimeter graph paper and another can be an inch graph paper. So if you take 4 centimeter grid in a centimeter graph paper and just compare it with an inch graph paper, again for 4 grids, that means 4-inch grid if you select in the inch graph paper, and you compare the size of the area which is being represented. This is where I would say very interesting, that if you take 2-3 pixels in centimeter grid and 2-3 pixel in inch graph paper, then you would find the distortion and the importance of the resolution. As you can see here this is the real exercise where you would find that this polygon is being represented into 2 different sizes of graph paper. So here there is smaller pixels, here it is the larger pixels. Now converting the same data into these pixels, assigning this attribute information to the larger pixel size, it is being shown in this way. So here you can see it is far different from the original data. The original image is like this, but the shape has distorted a lot here because the pixel size or the resolution of our depiction in raster format is larger. Whereas if we take finer resolution, the smaller pixel size, it is more like the original image. So that is what an important issue which we find, which we have to keep in mind in raster format. But still we use raster data because there are various other advantages which we would be discussing later on. But right now, on the basis of resolution, it is an important reason which we need to keep in mind for assigning attributes, details onto the raster data. Now again, this is another good example as to how we can handle the attribute information in the raster data. So here there are 3 land use classes which are depicted. One is said to be the urban area, and another can be the river, and the third one is the park. Now each of these land use classes, they are assigned the digital number, as you can see 10, 20, 30. Now why we have to assign the digital number? Simply because we all know that these data we are representing it in digital format. So for the system to understand as to what kind of land use is being represented in digital format, instead of this feature information like urban, river or park, we would assign them a specific digital number to them. And that digital number would result in transforming the whole of the raster data according to the digital number assigned to them. And since we know that 10 is assigned to urban, we will ultimately know that this digital number, which we may also assign a certain color, and that way the picture image will come for our better understanding. But when we will assign them the value of 10, 20, 30 or any digital number, that would be very easy for all kinds of analysis, because in digital, when we convert the feature information, attribute information into the digital number, then it is very easy to do analysis, as the system would be very conveniently transform and manipulate and analyze the digital numbers, which is the inherent characteristic of the computer system. So that is what we do in representing the attribute information in raster data. So attribute handling in raster data is done with each pixel is assigned a single value which represents a real world object. As I am saying, urban, river and park assigned as 10, 20 and 30 respectively. The pixel can hold this numeric data, and each pixel value in the raster here represents a feature class. like the urban, river or park. So 10, 20, 30, if I can magnify them and zoom it in then you can find that these 4 pixels they are representing 3 different land use classes, and these 3 different land use classes are also can be depicted through 3 different colors, and that way we make the raster image more colorful, more easily understandable, and efficiently the analysis can be done through raster data. Now, continuing with the raster data, how we rasterize it. Now, this is, I'm not sure as to how well you can see these images, but it's a very interesting example which I'm trying to depict here, where how we rasterize any geographic details into raster format. Here we are trying to represent again the 3 land use classes, the open space, river and built up structure in raster data format. So how we are proceeding with it? This picture will give you a good idea as to how data is represented in raster format. So here we are assigning 1 as the built up structures, 2 as the open space and 3 as the river, you see here. Then the first grid cell, the A block is representing the first grid cell which is acquired. The B is representing this grid cell, the raster format grid cell is placed on the land use map. So, for example, if there is any land use map, we are placing these grid cell over that land use map, which have built up structures, open spaces and river as features, which ultimately the raster data has to represent. Then what we will do in C here, you find that they would be assigned the land use class according to the pre-decided option for considering the land use allocation to the individual cells. So this is what we have done. So all the blank area, they have remained as blank, but we have not blank, it is the open spaces, but here there is the built up structure and this is the river which is flowing in between. Now here it is interesting, it is a linear feature, but depending on the size of a selection of the size of grid cell and the size of ground realities, we are finding that it is not a despite being a linear feature, it is being represented more than one pixels. Although it's a linear feature, but it is more represented in polygon because it has having many of the grid cells which have the width of 2 grid cells. So linearly grid cells are aligned, but horizontally also the grid cells have more than 1 pixels. So that is also can be explained as a polygon rather than river because of the resolution of the grid cells. And the third one is the open space. Now when we assigning these 1, 2, 3 pixel size, in the previous slide I assigned the attribute information in the form of 10, 20, 30. Here to be more easily recall as to what numbers we are assigning, what digit we are assigning, we are saying 1, 2, 3. So when we assign that in D, you may find that the value of this ground reality is depicted in this particular grid in D. Now again I would say that this D, assigning value as per assigned code, this is the method of rasterization. But as I have said previously also, that rasterization, if we adopt the coding as differently, then it might be represented in different way. Now here you see, for example, here we are coding the features when in each pixel, if only the specific land use class is existing, then only we will code them as specific land use class. It will be like this, it will be represented in digital number like this, 0, 1, 2, and the raster image will come like this. But if the coding is done in this way, where we are using the majority area, then you would find that these linear features will disappear in some of the pixels. And if we take the coding as priority, then again the linear feature would disappear. So again I would say that the same exercise will give you a good idea as to how the resolution or the size of grid cell play an important role in raster data format. So this picture will give you a good idea as to how a data is represented in raster format, and representation of three land use classes which we have taken as example: river, built up structures and open spaces, which the coding is done, but you need to take into consideration the inherent errors and consideration. Earlier we discussed an example showing what the effect of grid size on data in raster format was depicted. In the earlier example, I showed you that how the size of grid cell that brings some kind of error, or if we have smaller grid cell size, then it is depicting more accurately the information. Now here we are suggesting that if we take appropriate coding system, then the data would be more precise, otherwise there might be some distortion. So some data with larger pixel size would have distortion in shape and error in area calculation. Now here we are trying to show that how same grid size but considering different coding can distort the representation. But since generally the ground details are quite large and we use scale with larger ratio, so all these errors and distortions are negligible. But these example and images would give you a fair idea of raster data format and the rasterization process and the inherent quality of rasterization and the errors which are associated with it, and what precautions we need to take when we are rasterizing. That is very important, and you can understand very effectively in this particular slide.